Hi. Just as I did for the first time with lecture 26, here at lecture 27 I've decided to split it into 3 parts. I'd like to get back to 2 parts in future lectures, but it just seemed to fit better. This is lecture 27A that you're watching. It's about forced harmonic oscillators, basic examples with exponential and polynomial forcing. You can see lecture 27B is more about change of variables in linear systems of differential equations. We're going to do an example with a symmetric matrix, which is very special. It's going to be diagonalizable, but even more so, it's what's called orthogonally diagonalizable. It's a very important topic. And lecture 27C is about a very hard subject in general, Jordan canonical forms. Yes, we say Jordan, not Jordan. But we'll do an example, and in the 2x2 example we do, it's not too bad. It's the general theory that's pretty tough for that kind of subject. All right, on with lecture 27A. Forced harmonic oscillator ODEs. This first slide is general comments that are still important, and then after that we get into an example. So what is the general forced second order harmonic oscillator model? It's of this form. Notice the left-hand side is what we've seen before. The mass times the acceleration, the second derivative of the position with respect to time, plus b, that's the damping constant, times the velocity, the first derivative of the position with respect to time, plus k, the spring constant, times the actual position or displacement y. Before we've looked at homogeneous equations where the right-hand side was 0, now we are allowing a non-zero right-hand side, a general function of t. T is going to be our external forcing function. In lecture 28A, we're going to look at sinusoidal forcing functions, cosines and sines. That's the most interesting case to consider, but we're doing simpler things in this particular lecture. Especially in the sinusoidal case, I like to think of the external forcing as if you've got a mass going back and forth on like a table, it's like swinging the table back and forth like this if you're somehow able to do that. The right-hand side function g of t is called the external forcing function, and it is a function of time, and again, this is what makes this non-autonomous when this is non-zero, and I'm assuming this is non-zero here. The left-hand side is still what we've seen before. If we want to be more official about what it's called, it's a constant coefficient because m, b, and k are constants. Second order because it involves second derivative as the highest derivative. Linear, it is a linear differential equation. Linear operator is what I called it before, but now I'm going to add the word differential because the operator does involve a derivative, in fact a second derivative as well. It's actually a linear transformation between function spaces when you think of it that way. In other words, we could write t as a linear transformation from C2R to CR. I haven't talked about C2R before. What's CR? That's the vector space of all continuous functions, real valued. That means the real outputs, whose domain is the entire real line, say. We've talked about C1R before. That was the set of all, the vector space of all continuously differentiable functions defined in the real line and also real valued, where the derivative not only existed but is continuous. Here, I'm assuming it's in C2R, which means the second derivative exists and is also continuous. Twice continuously differentiable. I need to assume that so that when I take the second derivative of the input functions, I get a continuous function at the end. These are 2 different vector spaces. By the way, everything in C2R is also in CR. All twice differentiable, continuously differentiable functions are indeed continuous. This is a subspace of that. This transformation is defined by this formula. T of f is mf double prime plus bf prime plus kf. Looks kind of similar to the left-hand side here. I could have written this with y instead of f. I could have written t of y as my double prime plus by prime plus kf. Why am I writing it this way? Well, just to emphasize, I can plug in functions into this. You know, in differential equations, we always have this abusive notation. Sometimes the letter y represents a variable, a dependent variable. Sometimes it represents a function. But here I'm trying to emphasize that the input for the t linear differential operator is a function. I'm not saying what the input for that function is. I could call it little t, or I could call it something else if I want. I need to take m times the second derivative plus b times the first derivative plus k times the function itself. That gives me a new function where if f is in C2R, then this entire thing will be in CR. The solution, this is related to the differential equation. The solution space of the associated homogeneous unforced differential equation, where 0 is on the right-hand side, is the same thing as the kernel of this linear transformation. Linear operators, linear differential operators, are linear transformations between vector spaces. I'm not verifying it. It's based on the linearity of the derivative and also the distributive property. It would be a good exercise for you to verify. Yeah, the solution set of this is the same as the kernel, because the kernel is the set of all, well, functions in this case that get mapped to the zero function. The function whose graph is a horizontal line on the horizontal axis. That set is the kernel of t. And it's also the set of functions that satisfy this differential equation. That should make sense based on what we've said before. Since it's a second order equation, I mentioned, without actually stating a theorem, that the solution space is a two-dimensional vector space. It's a subspace of the infinite dimensional vector space C2R. That's infinite dimensional. There's no finite basis for this thing. But the solution space, the kernel of T, is actually a two-dimensional subspace. If we can find two linearly independent functions that solve this differential equation, then those two functions will span the solution space, which is the kernel, and they will form, therefore, a basis, and a general solution is an arbitrary linear combination of them. All stuff we've talked about before. But now, if I go back to the non-homogeneous equation, I'm calling it a solution set rather than a solution space for a good reason. The solution set of the non-homogeneous forced equation, the original one here, is, well, not a vector space, but it is a kind of generalized two-dimensional plane? Plane? Huh? Aren't the elements functions? Yes, they are, but it's helpful to sometimes imagine it geometrically. Inside C2R, which is, in a sense, parallel to the kernel. It can be imagined as a translation of the kernel, in fact. We're thinking by analogy here. We're imagining the kernel, the elements of the kernel, as being a plane. The points in that plane are actually functions, not points in the usual sense. It's okay, we can do that. It's abstraction, but we can do that. The kernel of T contains the zero function. It contains the zero vector. The solution set of the non-homogeneous equation, when g of t indeed is non-zero, it does not include the zero function, because if you plug the zero function in the left-hand side, you get zero. You don't get g of t when g of t is non-zero. So it can't go through the origin in this higher dimensional space, this infinite dimensional space C2R. But we can add a particular solution to a general solution of the homogeneous equation, and that adding of a particular solution, in a sense, kind of translates the plane away from the origin. Is it worthwhile to imagine such abstract vector spaces more concretely, like as planes? We will see eventually that it is handy to do that, especially near the very end of the course, where we get into talking about partial differential equations a little bit, and Fourier series, and what are called inner products, which are generalizations of dot products. By the way, I wanted to say, and forgot to at the beginning, that ultimately, very soon here, I'm going to be trying to wrap the course up. I'm aiming for lecture 35 or 36 to be the very end of the course. At the moment, we are in lecture A, is going into chapters 4, 5, and 6 ultimately in this book. We're starting chapter 4 right now by Blanchard, Devaney, and Hall. In the lecture Bs, I do want to continue sort of lingering in chapter 3, continuing to apply linear algebra to linear systems. We will eventually apply it to nonlinear systems too, though. All right, let's look at our example. We need to use the method of undetermined coefficients. Let's take an example initial value problem, this one right here. So I've taken essentially m to be 1, b to be 5, k to be 6, or if m were not 1 to begin with, I could divide everything by m, and then essentially b over m would be 5 and k over m would be 6. But it's easiest just to pretend the mass is 1 kilogram. There is my external forcing function and exponential decay. How in the world would you create a situation where you have such an external forcing function? We're not worrying about it. Y of 0 is 1 and y prime of 0 is 1, so if the mass is horizontal and I'm pulling it to the right of equilibrium, I'm essentially pulling it 1 meter from equilibrium because y of 0 is 1, and then I'm letting it go from rest because the initial velocity is 0. But I've got the external forcing. It's not going to act the exact same way as it would if this were 0 there. However, this function decays towards 0 pretty rapidly, so the behavior is actually not that much different than what you would see if this were 0 here. If this were something that does not decay to 0, as in the next example, then it behaves weirdly, possibly. So what do? Step 1. Find a general solution of the associated homogeneous equation where you make the right-hand side 0. It's not the exact same equation. It's just a related equation that's going to help us solve this, as we've done with, for example, first-order systems before. First-order scalar equations. So there's our corresponding associated homogeneous equation where the right-hand side is 0. We've seen that you can guess solutions of the form e to the st, I called them at first, but we saw that the s's were the same as eigenvalues for the matrix form, and so why not go ahead and call them lambda? Plugging in e to the lambda t and solving for a value of lambda that will make it work results in this thing needing to be 0. Essentially, you just translate the second derivative to a second power, the first derivative to a first power of lambda, and the function itself to a 0th power of lambda. Keep the coefficients the same. We've seen this before. Set that equal to 0 and solve for lambda. It's easy to factor in this case, so it's easy to see that lambda equals -2 and -3 are the values of lambda that make this a solution of this scalar associated homogeneous equation. And therefore, our general solution is a general linear combination of these two functions. These are two linearly independent functions. They do form a basis for the solution space of this associated homogeneous equation. Call it YH for homogeneous. We're not done though. This is not the general solution of the equation we're interested in, the non-homogeneous or forced equation. Step 2 is to guess a particular solution of the original using this method of undetermined coefficients. All right, so you got to guess. There are good guesses and bad guesses. See a 7e to the -4t there. Probably it's not a good idea to guess cosines and sines, because when you take the derivative, add 5 times take the second derivative, add 5 times the first derivative, and add 6 times the function. If y is a cosine or a sine or some combination, there's no way you're going to get 7e to the -4t. You probably should guess something involving e, in fact, e to the -4t. How about a constant multiple of e to the -4t? Call that constant a, as I've done recently, and see if you can make it work. See if you can choose a to make it work. So you've got to do what we've always done. Plug it into the left-hand side, substitute into this equation here, and set it equal to the right-hand side, which is 0. Excuse me, not that equation. It's this equation up here, because I'm looking at the non-homogeneous equation. Set it equal to the right-hand side, solve for a if you can. So here's the first derivative, here's the second derivative. I use the chain rule each time, getting an extra factor of -4 each time. Plug it into the left-hand side of the differential equation over here. So take y double prime plus 5y prime plus 6y. Simplify. It simplifies to this. Check it in your mind here. We've got the second derivative, which involves a 16a, plus 5 times the first derivative, which involves 5 times -4a, which is -20a. 16a minus 20a is -4a. Plus 6 times the original function, 6a gets involved. So we ultimately get -4a plus 6a times e to the -4t. And that's going to give us 2a e to the -4t. Set that equal to the right-hand side, this thing right here, goes right there. Solve for a is 7/2. If this is a solution, a must be 7/2, and in fact you can also check that if a is 7/2, it will be a solution. These really are equivalencies. Step 3. As a general solution of the original forced equation, non-homogeneous, add yh and yp, and then use that to solve the initial value problem. So here's the sum of yh and yp. There's yh, there's yp. I need to set y of 0 equal to 1 and solve for k1 and k2, but I also need y prime of 0 to be 0, so I need to find y prime. With the chain rule, you can check that's y prime there. Now set, again, 1 equal to y of 0, that's the initial position. Plug in 0 here, here, and here. You get e to the 0 in each case, which is 1, so you get k1 plus k2 plus 7/2. If you plug in 0 here, both for y prime and for t, you get 0 equals, e to the 0 still are 1, so you get -3k1 minus 2k2 minus 14. Solve that system of equations for k1 and k2. You can do row operations if you want, you don't have to. I did. So k1 plus k2 gives you the coefficients of 1 and 1. 1 minus 7/2 is -5/2, so I get the -5/2 on the right side of that equation. For the other equation, I've got a -3 and a -2, giving you the -3 and -2 there. The -14 can go to the other side as a +14, which is what you see. Now go to RREF, multiply row 1 by 3, add it to row 2 to get a 0 there. 1 times 3 is 3, plus -2 is +1. -5 times 3 is -15, plus 14, which is 28, is 13. Now multiply second row by -1 and add it to the first row. You get a 0 there. 13 times -1 is -13. -13 plus -5 is -18, or -9. Put it all together. There's your answer. Right there. So you should check the answer as well. Maybe you want to pause the video to check that out. At the end of lecture A here, I will use Mathematica to also double check it. I'll leave the Mathematica for the end of these lectures. I think that would be the best thing to do in these lectures. Let's do another example. Polynomial forcing function example. And let's also make the solutions of the associated homogeneous equation involve cosines and sines as well as exponential decays. That's going to happen when the eigenvalues are complex. So here's my non-homogeneous equation. So I've made the g of t function be t squared plus 3t plus 4. I made the initial condition be 0, 0. The initial conditions are both 0 for the position of the velocity. The mass is at equilibrium and not moving. Will it start moving? Yes, because of the external forcing. Even at t equals 0, this has a value of 4. And in fact, it increases as t increases. The external forcing increases. So, it even increases to infinity. What in the world is that going to do to the mass in the spring? You might wonder. Well, let's see if we can figure it out. So the general solution of the associated homogeneous equation, again, the unforced equation, is found in the same kind of way as the previous example. Guess e to the lambda t, plug it in, you get this equation for lambda. Here it's not so easy to factor, but you can use the quadratic formula right there. -2 plus or minus square root of 4 minus 8 over 2 gives you a complex number, eigenvalues. -2 over 2 is -1. Square root of -4 is 2i, because the square root of -1 is I. And 2i over 2 is 1i, or just I. We got the plus or minus sign there as well. These two complex conjugate eigenvalues, you can just take the one of them, -1 plus I, and use it to create a complex solution, yc, which you would initially write as e to the -1 plus I times t power. Then you can multiply the t through, and it turns out to be okay to use a property of exponents like this. And then you can use Euler's identity that relates e to the it to cosine and sine. Euler's identity gives you the cosine and sine. E to the it is cos t plus I sine t. I also multiply the e to the -t through the parentheses to get it there and there. And then, what do you do with this? You do want a real solution, so you want to get rid of the I. This thing is called the real part of the complex solution. This thing next to the I, not including the I, is called the imaginary part, but it is a real quantity. It turns out, I've said before, that these are two linearly independent solutions of the original homogeneous equation. Therefore, take an arbitrary linear combination of them, since the solution space of the homogeneous equation is going to be two-dimensional, and you're going to get a general solution of the corresponding homogeneous equation. Now we're on to a particular solution, a YP. This is harder because you got really, well, what kind of function could you plug in the left-hand side, the linear differential operator, to get an output of t squared plus 3t plus 4? You better guess a quadratic if you think about it. That's going to have three undetermined coefficients. I guess a times t squared plus b times t plus c? Yeah, that's what you need to do. And so you need to solve for the three undetermined coefficients, a, b, and c. The equations to solve for them end up being fairly simple. And I've got all the work in one big chunk here. There it is. So yp, guess at squared plus bt plus c. That's the only logical thing to guess. Okay, you wouldn't want a t cubed term involved, for example, because then 2 times y would give you a t cubed term. And the right-hand side doesn't involve any higher power than t squared. You also would not want to guess cosines or sines or exponential decays or growth. Guess this. There's the derivative, there's the second derivative. Plug it in. Going from here to here is a little tricky. I did it all in one step. You'd probably want to show a couple steps to make sure you don't make a mistake. Where do you get the 2at squared term? You get it from 2 times yp, 2at squared. The other two terms don't have t squareds. So you get this 2at squared. Where do you get the t term right there? You get it from these two, yp and yp prime, not yp double prime. You're going to have a 2 times bt there. You're going to have a 2 times 2at there, giving you 4a. 2 times 2 is 4, and 2b in parentheses multiplied by t. And finally, for the constant term, all 3 terms contribute. Yp double prime contributes 2a. 2 times yp prime contributes 2b. And 2 times yp in the constant term contributes 2c. Set that equal to t squared plus 3t plus 4. You want these to be equal no matter what t is. The only way that's going to happen is if the coefficients are the same. 2a equals 1, which is the coefficient of t squared over there. 4a plus 2b equals 3. And 2a plus 2b plus 2c equals 4. That's a system of equations. You could put it in an augmented matrix to do row operations to solve for a, b, and c. But we don't have to here because it's quicker to just see, hey, 2a equals 1, so therefore a is 1/2. Plug that into the equation. 4a plus 2b equals 3. A equals 1/2 right there. 4 times 1/2 is 2. 3 minus 2 is 1. I get 2b equals 1, and therefore b is 1/2. Plug a equals 1/2 and b equals 1/2 into this equation equaling, this expression equaling 4. Don't forget the 2c here. 2 times 1/2 is 1, another 1. Subtract 2 from both sides, you get 2c equals 2, and therefore c is 1. Put it all together, and yp must be this thing right here. So my general solution of the non-homogeneous forced equation is going to be yp plus yh. This function plus this function is going to be my general solution. I still need to solve the initial value problem. There it is. Yikes. It's going to be kind of bad to have to solve for the initial value problem. Actually, when you end up solving for k1 and k2, that's the easiest part. The hardest part is right at the start to take the derivative of this. You do need the product rule, because you got a product there and there. So, for example, to differentiate this, think of k1 e to the negative t as the first function and cosine of t as the second. Negative k1 e to the negative t is the derivative of the first, and there's the second. Plus the first function, k1 e to the negative t times the derivative of the second. The derivative of cosine of t is the negative sine of t. Okay, do the product rule again with this next term. So this one gives you these two terms here when you differentiate. This one gives you these two terms when you differentiate as well, including that minus sign there. Differentiate this part, gives you t plus 1/2. Now plug in the initial conditions. It's actually fairly easy to solve for k1 and k2. E to the 0 is 1, use that. Cosine of 0 is 1, use that. Sine of 0 is 0. A bunch of stuff goes away. Also, when you plug in the 0 there, you get 0. You end up getting, using the first line there, 0 equals k1 plus 1 when I plug in 0 up at the top here. And with the blue line here, when I plug in 0, I get negative, 0 is negative k1 plus k2 plus 1/2. So therefore, from this equation, k1 is negative 1. And from this equation, k2 is k1 minus 1/2, which would be negative 1 minus 1/2 is negative 3/2. And this gives you your final unique solution of the original second order initial value problem. The spring breaks. Why? Because the graph of the position in blue and the velocity in red, well, the position goes off to infinity. The spring keeps the mass keeps moving to the right, and faster, in fact, the spring is going to break. That's the prediction here with this model. This would not be a valid model after the spring breaks, but we can see this is going to predict the spring will break. Please excuse the pun. You also can graph these things in a phase plane based on a systems approach. However, it would be a non-autonomous system, and the vector field will change. We will look at that a bit in lecture 28A. This is the end of lecture 27A. Thanks for watching.